So our last topic is colloids, and colloids are dispersed substances, not dissolved. So what that means is you have small groupings of the colloid, or colloids could also include very large molecules like hemoglobin that actually are large enough to scatter light. And so examples of colloids include fog. We see plenty of that in the valley when the liquid is dispersing into the solvent, which is air, and that's what creates the fogs. It's actually very tiny water droplets that are being dispersed throughout the air. Smoke is also an example of a colloid where the particulate, it's actually small particles of from combustion processes are created. So little chunks of carbon or residual from combustion are actually dispersed into the air, and then water droplets coalesce onto those, and that's what creates the colloid. And then there's an example for another example, for example, whipped cream, which is considered to be a foam, right? So these are aerosols. This is a foam. A foam is actually a gas dispersed into a liquid, so when you get whipped cream. And there's other examples. This is simply an excerpt from a table in the book. Soap is also a colloid. Soap, for example, sodium stearate is what technically is a soap. It's actually produced from the action of sodium hydroxide or potassium hydroxide on fat. But this is an example of sodium stearate. Contains 18 carbon atoms. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I think I miscounted in there. But there should be 18 carbon atoms in here. And then it has a carboxylate functional group on the end. That's a carboxylic acid group that looks like this. Very similar to acetic acid. Has a negative charge. This part is very strongly polar. Now this part is very strongly nonpolar, if you can be strongly nonpolar. And when you take soap and you throw it in water, then what ends up happening is the nonpolar parts are hydrophobic. And so what they do is they get away from the water. Hydrophobic is the term we use for things which don't like to mix with the water. So this nonpolar region of the soap molecule tends to hide itself away in a structure known as a micelle. So the outside part is the polar head, and then the long chains, what we often refer to as the tails, all point towards the inside and create what's this sort of spherical structure called a micelle. Now, this is the structure of a soap molecule, or soap as it takes when it goes into water, and that's why it creates what's called, again, a colloidal dispersion, a dispersion of molecules within water. If you take a light and you shine it on a soap solution, what ends up happening is that the light will scatter in the soap solution here. And this is just a water on the other side, a little bit of food coloring in it, I believe. But the colloidal dispersion, you can see in the soap solution this sort of scattering of light. That's the brightness that you see in the solution. What's actually happening is the light waves are coming in and striking the particles and then leaving the sides of the solution, so it actually looks like it glows. So soaps will do this. If you take a soap solution, you can do it with the laser. It's a little harder to see with the laser because it's so intense, but you can do it with a laser and you can see the scattering of light that is created when you make a soap solution. Well, these micelles are actually the reason why soap works to remove grease from food, containers that have contained food that has grease. So this is a really old video, so it's a little low quality, but it gets the point across pretty nicely. This represents a micelle from soap, and this represents a glob of oil, let's say on a piece of fabric or on a dish. And this is how the soap actually acts to remove this oil from the surface.
A soap micelle consists of a group of surfactant molecules with hydrophobic tails pointing inward and hydrophilic polar heads pointing outward. The micelle absorbs nonpolar oily liquids, and carries them away as an oil in water colloidal dispersion.
So the nonpolar portions of the micelle actually absorb the oil droplet from the surface, and because it's charged on the outside, it effectively masks the nonpolar region on the inside. Micelles are also used for a number of other interesting applications, and they're being looked at for drug delivery mechanisms because you can put something that's nonpolar on the inside and dissolve it into a solution and make a suspension out of it. Anyways, that about does it for the lecture. If you have any questions, you feel free to send me a message.